All right, let's tackle one of the most brilliant and, let's be honest, brain-bending ideas in all of science, Albert Einstein's theory of relativity. I mean, this is a concept that completely rewrote our understanding of space, time, gravity, pretty much everything. So let's dive in. And we're going to start somewhere you might not expect, with Buzz Lightyear. In his movie, he takes these high-speed test flights, and every time he comes back, he finds out that years, sometimes decades, have passed for his friends, while for him, it's only been a few minutes. It's a classic sci-fi idea, right? But that really gets you thinking, is this just Hollywood magic? Or could time actually tick at different rates for different people? Well, here's the crazy part. Thanks to Einstein, we know it is astonishingly real.
Okay, so when people say relativity, they're usually talking about two different but connected theories. First, you've got special relativity. That's the one that deals with really high speeds, like Buzz's spaceship. Then there's general relativity, which brings gravity into the whole picture. We're going to look at both, starting with the one that explains Buzz's little time travel problem.
First up, special relativity. This is the theory that unpacks the seriously weird rules of the universe when you start moving at incredible speeds. Now, this whole theory is built on one single radical idea that completely shatters our everyday intuition. And it's this: the speed of light is the ultimate cosmic speed limit. It doesn't matter how fast you're going or who is watching you, light always travels at the exact same speed. And that simple fact has some really, really strange consequences. And the most famous consequence is something called time dilation. To put it simply, moving clocks run slow. The faster you move through space, the slower you move through time, at least compared to someone who's standing still. This is exactly what was happening to Buzz Lightyear. Okay, but why? Why does this even happen? To really get our heads around it, let's use a classic thought experiment. Imagine we have a clock, but instead of gears and hands, it works by bouncing a little pulse of light between two mirrors. Each bounce, up and down, is one tick of our clock. So let's break this down. First, meet Mancy. She's an astronaut inside a super-fast spaceship with our laser clock. From her point of view, inside the ship, that light pulse is just going straight up and down. A nice, short path, we'll say 10 meters. Simple enough. But now, let's look at Kelsey. He's standing still on a planet, watching Mancy's spaceship zoom by. From his perspective, the spaceship is moving forward, so he sees that same pulse of light travel a much longer, diagonal path to catch up with the mirror. And here is the absolute key to the whole thing. Remember the rule? The speed of light has to be the same for both Mancy and Kelsey. So if Kelsey sees the light travel a longer distance, but at the exact same speed, well, then more time must have passed for him to see that one tick. From his point of view, Mancy's clock is literally ticking slower than his. That, right there, is time dilation. Okay, so we've established that speed can literally warp time. But what about gravity? I mean, that's a pretty big deal in the universe. For that, we need to turn to Einstein's second and even bigger theory, general relativity. General relativity gave us a completely new way to think about gravity. See, Einstein realized gravity isn't some invisible force pulling us down, like Newton thought. Instead, he said that massive objects, like planets, stars, you name it, they literally bend and curve the fabric of reality itself, a four-dimensional thing he called space-time. I know, that's a little hard to wrap your head around, but think of it like this. Imagine the universe is a big, stretched-out rubber sheet. If you roll a marble across it, it goes in a straight line. But now, place a heavy bowling ball in the middle. The sheet curves down. If you roll that marble again, it'll still try to go in the straightest line possible, but now that path is bent by the curve. That, in a nutshell, is gravity. I mean, this was a huge, huge shift in how we see the universe. So let's just quickly compare this new idea of gravity with the one we all learned about in school from Sir Isaac Newton. So here's the fundamental difference. Newton pictured gravity as some kind of mysterious force, an invisible rope pulling an apple down to the earth. But Einstein saw it as geometry. The Earth warps the space-time around it, and the apple is just following the most direct path it can through that warped space. It's not being pulled, it's just rolling down a curve in the universe itself. Okay, I know what you might be thinking. This is cool, but it sounds like really abstract, theoretical stuff. Does any of it actually matter? Oh, it matters. A lot. Both of these theories have very real, very practical effects on our world. You see, general relativity didn't just give us a new story about gravity. It made these incredible predictions that Newton's laws just couldn't handle. It perfectly explained this tiny wobble in Mercury's orbit that had stumped astronomers for years. It predicted that gravity could actually bend light. We call that gravitational lensing now. It even predicted the existence of things as wild as black holes and ripples in space-time itself, gravitational waves, which we finally detected in 2015.
And get this, just like speed, gravity also messes with time. It's called gravitational time dilation. The stronger the gravity, the slower time ticks. So a clock on the beach at sea level literally runs a tiny, tiny bit slower than a clock on top of a mountain. It's a real, measurable effect. And here's why this matters to you right now in your pocket. Your phone's GPS works by talking to satellites. Now, those satellites are moving really fast, so special relativity says their clocks should tick slower. But they're also in weaker gravity than we are, so general relativity says their clocks should tick faster. To get your location right, the GPS system has to constantly adjust for both of these effects. Without Einstein, your GPS would be off by several kilometers every single day. It'd be totally useless. So after all this mind-bending talk about warping space and slowing down time, what's the single biggest idea we should really walk away with? It's really this. The universe isn't some fixed, static box that things just happen in. The universe itself, this fabric of space-time, is an active player in the game. It bends, it stretches, it ripples. Its shape tells matter and energy how to move, and in turn, that matter and energy tells space-time how to curve. And that leaves us with one last, kind of awe-inspiring question. We've just learned that one of the most fundamental forces we experience, gravity, is actually just the shape of the universe. So what else might be out there, hiding in plain sight, disguised as the very geometry of reality itself? Something to think about. Thanks for joining us.